Hello, welcome to numerical ship and offshore hydrodynamics. Today we have the lecture 47. Today we are going to discuss on time domain planning method, of course, but for the non-linear case. So, today we are really in previous class we discuss till previous class we have to discuss the linear part, and as I mentioned that if you use the time domain formulation in earth fixed system, it may not be that difficult to include some sort of nonlinearity into the solution. So, let us see that what sort of nonlinear thing actually we can include in the linear time domain solution. Okay. And this is the keyword that you are going to use to get this lecture. So, let us start the thing. Now, here you can see that I wrote this is level 2.5, because before I explain what is level 2.5, definitely we are going to discuss what is level 2, level 3 and level 4 and level 1. Right. Now, in level 2.5 it is it is between the level 2 and level 3. So, we will discuss that what is the other levels. Now, what here the focus is that what nonlinear we can include. Now, if you remember that in our case we are taking this total phi is equal to that phi incident, right, and then plus phi disturbed. Now, when we do the linear thing, what we do is we use the linear z equal to 0, that free surface, right. And then this is actually that our body up to z equal to 0, and then I discretize the body up to z equal to 0. So, over the time that in boundary conditions, when we apply the boundary condition, all the boundary conditions about z equal to 0. So, therefore, this geometry, if I call this geometry G, okay, now G is the Green's function. So, I can call geometry is geom. See, geom is not the function of t, because this geometry is invariant under time, because we are doing the linear analysis. And then, but when you do the non-linear analysis, at that particular time we do consider following things. What are these? First, we consider the exact free surface, exact or exact weighted surface. And then at second, we incorporate the motion or body motion. So, these two things actually we consider, right. So, when we use these two things, then the geometry is no longer remain the invariant. Why? Because very simple reason. If let us say this is my, let us say the free surface. So, now what we are considering, the ship is actually under this the wave. So, let us just make some rectangle, then it is easier for you, and then we consider, right, kind of this situation. So, what is happening here? Now, you can see this weighted surface is continuously changing with respect to time. This weighted surface is continuously changing with respect to time. Now, if you do the linear thing, if you do the linear analysis, that time your this ship is always, this triangle is always look like this. So, this under weighted surface does not change with respect to the time. So, this is the first thing when we incorporate the nonlinearity. So, and also the Fruit-Kiln law force, if you remember, we assume that this Fruit-Kiln law force we have already discussed, right. It is always it is we do up to z equal to 0, right, and we assume that whatever the fruit law force at z equal to 0, that the same is happening at z equal to a also. See, this is our underlying assumptions of the linearity. Now, here the major challenge is when you incorporate the wave, then in the exact weighted surface, how I can define my fruit law force. And similarly the same, it is same for the hydrostatic force also. Earlier this is my thing. So, we can go with the definition C33. Let us only talking about the heap, let us forget the other part, okay. Just talking about the heap. Now, when you do the exact weighted surface, so that means you have to calculate the exact static force, and therefore, this it is no longer C33. So, at that time you must consider the resultant static force, which is FSR, which is the weight minus the static force, the buoyancy. So, these are the change that you have to consider while you are doing with the nonlinearity. And the second part, and that is actually these things, when you do started these things, this started with the level 2. So, I just write it L2. So, if you only do this much, then it is actually the level 2. Now, when you just modify the body boundary condition little bit, actually this is something that new that is so when you make some kind of approximation in simplistic way, then it becomes level 2.5. So, now when you incorporate this part, this becomes level 2.5. Now, why it is 2.5, why it is not 3, why it is not 4? So, let us try to understand this. Now, let us see that this is our conventional level. So, it is level 1, level 2, level 3, level 4, and then the fundamental questions comes over here, why I am concentrating on the level 2.5, of course, and why you are not going with direct level 3, level 4, right. So, we discussed level 2, linear level 1 already we have discussed, right. Though still we have to figure out many things, at the end we are doing it when do the actually computer coding, some logic, everything, how to do that, this definitely we are going to discuss at the end, but at least at some level we know what is level 1, what is what we are going to do there, what is the difficulties arising when it is numerically unstable. If it is numerically unstable, then how to make the code numerically stable, all this discussion we have done, right. Now on we try to find out that the nonlinear thing like the level 2, we already discussed the level 2. So, whenever we discuss level 2.5, it includes level 2 and level 2.5. Now, here we were going to definitely answer at the end why we are using this level 2.5 and what is the advantage of level 2.5 over the level 3 and level 4. Okay. Now, let us try to understand all the levels one by one. Now, in level 1 we have two components. If you remember, my total potential phi t is divided into phi incident plus phi disturbed, or we can say simply phi. Now, if you do that, then you can see here in this picture that phi incident, as I know that Fruit-Kilder force that we have computed on the mean free surface. Now, if you remember that when it is z equal to 0, we called as a mean free surface, and when you call the z equal to eta, we call the weighted exact weighted surface. So, this normally we called at Z 0 and this we normally called at Z b, right, or body, or sometimes we can call it S 0 and we can call sometimes this as S b. So, these all the notation that we have to understand what is the meaning of the notation. Now, in case of a level 1, our Fruit-Kirchhoff force, diffraction force, radiation force, all the force actually we have computed, calculated at mean free surface or at z equal to 0, right. And then it is actually consistent. Why? Because then I take a linear thing and I can linearly add the thing. Now, when he remember here one very important like concept, when even we say it is a non-linear, it is not purely non-linear. Why? Because you see that in non-linear you cannot add, right, like a plus b, it is not possible for a plus b whole square, you cannot do like a square plus b square, you cannot do that, right. Now, so therefore, so when you do a plus b whole square is a purely non-linear thing, because as you know that we really can't do this equal to a square plus b square, it is not possible, but a plus b or some force f a plus f b, now suppose we have some force a is a component, b is a component, we can simply linearly add. So, this is something we called a linear. Now, when you say the non-linear, one has to understand that when you say the non-linear, it is not purely non-linear. Now, what is purely non-linear? So, if I take phi total, a sole phi, and we do not take any component of it and we are not adding anything, then we can call it is a purely non-linear problem. Okay. But however, if you see here in the level 2, what we are going to do as follows, still we are taking my total phi, phi t is equal to phi I plus phi. Now, when you do this, it indicates that I am going to use the linear superposition technique. Now, when you do the linear superposition thing, then I cannot call is a non-linear, is it not? But still, if you go through all this journal paper, they say that is a non-linear problem, non-linear time domain panel method. You can number of paper actually you can get. In fact, in reference after end of this course, I listed out all this reference. There also I will show you that very commonly we use the term that non-linear, right. So, then you have to be very careful and you have to be very sure that it is not purely non-linear. Now, let us say what is happening here. Now, here when you solve this phi I, when you solve this phi I am using the exact weighted surface. Now, when I am using the exact weighted surface, so it is a some part that force I am getting, I call that force is non-linear. So, therefore, this we can called as component wise non-linear. Okay, but it is not purely non-linear. So, here what we are doing in level 2, when I calculate the Fruit-Kirchhoff force, that time I am using the exact weighted surface. However, that radiation or the disturbed potential which gives me the radiation and diffraction, which gives me the radiation force and the diffraction force and also the steady force and also the steady part of it. So, when you calculate this, that time I am using our exact weighted surface Z 0. So, here level 2 is that when we do this phi I and we are using the exact weighted surface, but when you do the phi we do not use the exact surface. Now, what is the advantage? Now, here you see in level 1 it is said that level 2 is most advantageous for all levels. Okay. Why it is so? Because you see here since I am only using this component, the Fruit-Kirchhoff force part of it actually, and I am not touching the second part. So, I am not touching the second part, then still I can use the same invariant mesh. What is the meaning? Okay, let us see. It means that suppose I have this panel, I have this panel. Okay. Now, it is about the z equal to 0 and I am, so this paneling I am not changing over the time. So, this geometry I can call geom. This is not also again it is not the function of t, no, not like that. So, because it is here. However, if you remember, now if I do the time domain, I am using the simple phi and that it is a analytical solution a g by omega into e to the power k z into sin k x minus omega t, something like this, that is what I am using. I am using a analytical function to calculate the pressure on a analytical surface, right. So, to do that we really no need to do the remeshing all the time, because here which is purely numerical, this part that actually I am doing for the radiation diffraction problem. However, that we can use a separate meshing for the Fruit-Kirchhoff part. So, that means we do not disturb this part, we are using the simple paneling and we are using it for solving this particular portion, and for this second part what we could do actually, I can have the second geometry. I can have the second geometry which actually or second paneling, rather say second paneling. I can use the second panel which is paneling up to the main deck. So, this paneling is up to the main deck. So, what is happening if it is up to the main deck, then I use this, I can say the panel set 2, I can call this panel set 2 P set 2. I use this panel set 2 to calculate the nonlinear Fruit-Kirchhoff forces. However, I am using the panel set 1 to calculate the linear force. So, thing is that at this particular time that I am using two different mesh, because this mesh and this mesh is not at all connected. Okay. These two mesh are not connected, because I am from this mesh I am getting the component phi, the force because of the phi, and then with this mesh I am getting the force because of the phi I, and nowhere phi I and phi I are connected to each other. So, I can simply use the linear superposition between these two. So, therefore, this is the level 2 and this is advantageous because I am not doing the paneling, I mean the paneling for the phi, I am only doing the paneling for the the incident, and which is easier. Why? Because if you look at the next level, here what actually I am doing, now you see I am incorporating the motion of the body. So, now here you can see that I am incorporating the, let us say, Z 3 and Z 5, and I extract that what is the exact weighted surface at z equal to 0. Now, this is little bit tricky and little bit complicated too, and so we need discussion on this. Here what we are looking here, you can see. Now, I just write down that body boundary condition, which is del phi del n is equal to V n minus del phi I by del n, and this must apply at z equal to 0, otherwise I cannot use the Green's identity, I cannot use the Green's theorem. So, since I cannot use the Green's theorem or Green's identity, so therefore, all the time I need to know that what is the mean weighted surface. Now, in linear it is very consistent with thing, we do not change the geometry, it is always same, we are not incorporating the vessel motion into the body boundary condition. However, here what we are going to do is, we are incorporating the vessel motion into the solution and each moment. So, at each time instant t, I try to find out what is my weighted surface, I can call that S b is the function of t now, right. So, also, or we can say that it is, we can say at it is S 0 at t, because I am always try to figure out what is the mean weighted surface. Now, this surface with changing with respect to time. You see, it is so complicated, we are going to discuss all this problem in future classes, but at again as a surface level, at least we understand one point is that here I require paneling at each time instant. Right. So, here we need remeshing, we do remesh at each time instant, and also we need to remesh this as well. Now, therefore, this level 3, in level 3 I am solving this phi I on exact weighted surface, but here phi at exact mean surface. Here I am not taking the weighted surface, right, I am cutting it at z equal to 0. So, I am taking that what is the exact location of the ship, and then I intersect at z equal to 0 and I figure out what is the weighted part, and then I solve phi for this. Now, frankly speaking, this body nonlinear or the level 3 is not very popular and not very consistent also, and people normally do not use the level 3 as such, okay, because you see that it is a complicated thing, like it does not have any solid mathematical background, like when till level 1 I have the solid mathematical background, but from the level 2 onwards we do not have the solid mathematical background. Okay. So, so everything is intuitive, and then there is no solid mathematical background to figure out this is consistent. And if you ask me that, I cannot say that if you use it, it is what I call like give you the exact feel of the physics, that is also not possible. We try to incorporate some kind of nonlinearity, we have some kind of approximation into it and we try it, right. However, people find that this body nonlinearity, it is not that useful, and this method that is why not that popular. So, people using we call the weak scattering problem and which is the level 4. Now, here at level 4 what we are doing is, now if you see that if you consider level 3, this exact weighted surface is not same for both the force, and that is why people have problem. Now, when you calculate this phi I, this surface, and we calculate the phi, there is a lot of difference. Now, here we try to in level 4 actually try to sort it out this problem. How we do that? We take this weighted surface, then actually modify the shift geometry for the phi such a way that weighted surface become invariant. Now, what is exactly level 4 is that I am solving the phi I in the exact weighted surface, and also I am solving the Diephx potential phi also at exact weighted surface. Now, how it is possible? Because at Green's function g is only valid for at z equal to 0. If you take z equal to eta, you cannot use the boundary element method. So, to use this you have to have it is on the mean weighted surface. Then how it becomes exact? Now, what we do? We use some transformation. Now, what is the transformation? You see, if you look at this figure, the left hand figure, let us say call this figure 1 and figure 2, you can see that here this is the weighted surface, it is little bit top. So, what we are doing is we make it down, and then actually then this profile which is at eta 1 we are doing it a downward here, and then this part actually you can, it is not that exactly I am just making it this way, it is not like that. We use some transformation which convert this into figure 1 into figure 2 such that weighted surface become invariant. Okay. So, this is how we can do the paneling. So, let us keep it. Now, this will again going to discuss later on. So, now you see here this is what I am talking about, the exact weighted surface. Now, you see in the top figure I can see the exact weighted surface, and in the bottom figure it is the transformed weighted surface. So, that is actually here we are using. So, what we are using my del phi del n that I am using in this particular thing. Now, you can see that here over the time again the panel got changed. So, we need to do the remeshing, right. So, it is not only the remeshing, right, and it also about the rate of change of phi, that rate of change of phi, not phi I we are not, because the analytical expression, but phi is a purely numerical thing. So, now if I change the paneling, then how the phi also change, that also we need to consider. So, this is I mean we are really do not go into that complexity. I am just telling you that where actually this 4 level does. Okay. So, it is just to you can say like a very elementary information about the level 2, level 3 and level 4. Now, from the next class onwards we are focusing on the level 2.5, and that particular time we are going to discuss very elaborately about the how to calculate the Fruit-Kessler force on the exact weighted surface, how to calculate the body boundary condition from on weighted surface, not mean free surface, how to incorporate all these things, that actually, and why and where this level 2.5 is different from level 2 and level 3, what is the advantage and all, everything we are going to discuss in the next class. So, today we only discuss about the all 4 different non-linear level, and what is the advantage, disadvantage, those things we are going to discuss from the next class, and then why 2.5 is more beneficial over all these 4, I mean not 4, level 1 is a linear, all 3, that means 2, 3, 4. Why 2.5 is beneficial, that also we are going to discuss from the next class. Okay? Thank you.